All right, welcome everybody. If somebody could work on the lights, getting those down a little bit, that'd be great. Thanks very much. So welcome everybody. My name is Cynthia Blankenship. I'm president of the Geologist Jackson Hole, and I work on the speakers committee as well. And for those of you here in the library, I hope you've enjoyed the advertising. Too bad for you guys at home. Please remember to silence your cell phones or turn them off. And also, if I could ask you to hold any questions to the end of the presentation, that'll help keep us on time and keep the flow going. For those of you on Zoom, please direct any questions to me, Cynthia Blankenship, via the chat feature, and we will address those at the end of the meeting if we have time. I'd also like to encourage everybody to join JJH if you haven't already. As a member, you get to come to our famous barbecue for free, and you get to come on our exclusive field trips. So, and then also, of course, you help support our snacks and our scholarships and everything else. So, we next month, we have an exciting program already lined up for 2025. And our February 4th speaker will address how warm is too warm for Antarctica. 3 million-year-old lessons from a higher CO2 world, given by Christina Resselman, originally from Bozeman, and now at the University of Otago in Dunedin, New Zealand. And she will be here in person to give this talk, so one not to miss. Now let me go ahead and introduce our speaker, Jim Woodmencey. I think most of you know him or know who he is at least. Probably doesn't need much introduction, but let me just give you a little bit about his background. So Jim is the owner and chief meteorologist at mountainweather.com. He received his degree in meteorology at Montana State University, and after graduating in 1982, he moved to Jackson to take a job in Grand Teton National Park, and ended up working 14 summers as Jenny Lake climbing ranger. Jim spent one winter working as a forecaster at the Alaska Avalanche Center in Anchorage in the mid-1980s, and after that he worked 20 winters as a lead guide and forecaster for high mountain helicopter skiing here in Jackson. Mixed in there, he spent 20 years broadcasting weather on the local radio stations in Jackson, as well as writing a bi-weekly column for the Jackson Hole News and Guide. Jim has over 30 years of experience forecasting the weather here in Jackson and for climbing expeditions worldwide. He continues to share his knowledge by teaching weather courses to the public and to the United States military. And so we are very lucky to have Jim educate us tonight. So thank you, Jim. Over to you.
All right. Thank you, Cynthia. Thanks for coming out tonight here, and thanks to folks on Zoom. I assume you can see me. You don't have to be able to see my mug, but I'm here if you need to see me. But tonight what I want to do is introduce you to the atmosphere and talk to you or explain how the weather works, how the physical and chemical properties of the weather, how they kind of control our weather. And it's going to be a little bit like a crash course in meteorology. It'll be like a college level introduction to meteorology, but without the calculus and differential equations, if that's okay with you. It's fine with me. No, there'll be a quiz, so be ready for that. So Meteorology 101, for those of you who have never studied the weather at all. Some of you perhaps know more than I do about the weather, and this will be a good review. All right, we'll take it from there. First thing I'll do is I'll sort of describe the makeup of the atmosphere. I'll talk about different air masses that develop and why they do that, and then show you what high and low pressure are. You hear those terms all the time. And I'll explain that in a little bit of detail, and then also talk about what the jet stream does and how it interacts with the weather that we get here on the surface. Right. First thing, the atmosphere that we're dealing with, where the weather is contained, is only about 50,000 feet thick. The lowest level of the atmosphere is known as the troposphere. It extends much higher than 50,000 feet until you hit the stratosphere. So if you've ever said, I'm going to send you into the stratosphere, you're sending somebody pretty far up there, over 100,000 feet in the atmosphere. But where our weather is only about 10 miles thick. Above that, you kind of run out of moisture to make any clouds. Periodically, you'll get thunderstorms out in the plains, maybe that'll extend above 50,000 foot elevation, but very rarely. So 50,000 feet is about as thick as it is. And if you can imagine that circling the whole globe above the Earth. It's made up of mostly nitrogen and 21% oxygen, so we can breathe. And then the other most prevalent gas in the atmosphere alongside those two is argon. Other gases that are very popular these days would be carbon dioxide and methane, CO2 and CH4. They're in very, very small percentages, but they do interact with the sun and the atmosphere and all that. So we'll talk a little bit about those towards the end of the presentation. But the one gas in the atmosphere that's more than those, and the next in line here, and actually sometimes in quantities greater than argon, would be water vapor. And water vapor is the invisible form of water. Water has three phases, right? Solid, liquid, and gas. And it can present itself in all three phases in our atmosphere. When it's in the water vapor phase, just the gas phase, it's invisible, just like carbon dioxide and methane would be invisible as well, and oxygen. All these gases are pretty much invisible. The only one that makes itself visible is water vapor when it condenses into a cloud or makes ice crystals in the upper levels of the atmosphere. What's kind of interesting to me, sort of fascinating really, is if you put this in perspective, that 50,000 foot of thickness that surrounds our globe, in relative terms, is about the same as the thickness on the skin of a tomato. It's a really thin skin that contains our weather when you put it in that perspective. And the other thing that's amazing to me is this small amount of water vapor, and around the whole globe on any given day, over any given location, it might average 1 to 2% of the total makeup of the atmosphere would be water vapor. That would include clouds and precipitation that's going on. Over the tropics, if you measured it, it might be like 4%. Over the desert, it might be even less than 0.4%. But on average day, average place around the globe is 1 to 2% of the makeup of the atmosphere is going to be water vapor. But that little percentage of water vapor creates all of our weather. From a light snow shower like we had the other day, to a downpour from a thunderstorm, to a hurricane or typhoon or tropical storm. So it's spit in the ocean, basically, when you think about that. The maximum is about 4% of the total makeup can create the largest storms that we get on Earth or in Earth's atmosphere. To put all the gases, it's not really a pie chart, it's more of a donut chart. Nitrogen and oxygen, the greatest amounts. And then water vapor is the little blue wedge. That'd be the next most, next to argon, the purple one. And then all the other gases are pretty much trace gases, if you will. But we'll talk about those and how they interact with our weather. So can anybody answer this question for me? One word. Thank you. The sun drives everything. It heats the earth. It heats it somewhat unevenly. One side's getting heated during the day and the other side's in the dark. So it's cooling on one side, heating on the other throughout the day. It changes seasonally as we go around the earth, because the axis of the earth, and Mike Adler probably could tell me how it happened when we got hit by some other planet or something and it tilted us. But we've been tilted for a long time. And so that tilt of our axis kind of changes things, especially in the summer and the winter, where in the winter months, the northern hemisphere is tilted away from the sun, and in the summer, we're tilted towards it. And then in the spring and fall, northern hemisphere, spring and fall, we're kind of evenly distributed with the amount of sunlight that we get from the North Pole to the South Pole. It's, you know, maybe really low in the sky down at the South Pole or the North Pole, but, you know, at midday, but it's still putting some daylight onto the whole planet, basically, during the equinoxes. Equal day, equal night is what that means. The tilt is about 23.5 degrees. And that, I'll talk about that tilt and the significance of it in a minute. But I wanted to talk about the fact that, and most people I hope know this, that the Earth revolves around the sun. It's a relatively new concept. It's only been around for less than 200 years, confirmed. Galileo, back in the early 1600s, proposed this theory, and he published a paper in 1632 saying the Earth, describing how and why the Earth revolves around the sun. Prior to that, it was believed that the Earth was the center of the universe and the sun revolved around us. When we look outside, we see the sun go by, it all makes sense, right? It was actually Copernicus who first proposed this about 100 years before Galileo. But Galileo became the rock star of all scientists back in the 1600s. And the way you become a rock star is everybody calls you by your first name. Galileo. Oh yeah, we know who he is. You know, it's kind of like Madonna or Elvis or Prince. He was a scientific rock star. Copernicus, who came up with the theory 100 years before, that was his last name. His first name was Nick. So his theory wasn't, you know, as good as Galileo's. He was more of a rock star. So the problem here was, you know, and this was what we would call today settled science. And they basically wouldn't accept the Copernican theory or Galileo's paper. And I hate to say this, but it was the Catholic Church that controlled science back then. And so they tried him and convicted him of heresy and confined him to house arrest for the rest of his life, which he only lasted another 8 years after he published that paper, or after he was convicted, I should say. Unfortunately, from then on, they still thought the Earth was at the center of the universe, and that's the science. It was done. That's what it is. Everybody had to accept it. And I don't know how the Pope got involved with science, but he was. And it wasn't until 1758 that they finally accepted that this theory might be true and allowed his papers to be distributed, and that the science advanced. And it was 1835. This is when people were still coming out west and settling the West before the Pope, the Vatican, agreed, okay, yeah, I guess we give up. You're right. The Earth does revolve around the sun. I just find this to be a fascinating scientific story in itself because it has to do with weather. It has to do with the sun. It has to do with our seasons. It has to do with all of those things. So you know, it's only 190 years ago that we finally said this is going on. It was, you know, several hundred years before Galileo, the Earth was flat. You remember that? They still haven't disproved that one. Well, look at the weather maps. They're all flat. Okay. And that one other thing here, it wasn't until, to finish this story and get on with the presentation, it wasn't until 1992 that Pope John Paul II offered what I would call a weak apology to Galileo and said he was somewhat mistreated at the time. Jesus. All right. So that's the backstory, that we do revolve around the sun. I think that's settled now. That 23.5 degree tilt is critical this time of year in December during the solstice. The sun would be directly overhead right at the precise time the solstice occurs over the Tropic of Capricorn, which is 23.5 degrees south latitude, right? The Arctic Circle is 90 degrees minus 23.5 degrees, which puts it at 66.5 degrees. Okay. In the summer, the opposite would be true. We're tilted towards the sun. So on the June solstice, right over the Tropic of Cancer at 23.5 degrees north latitude, that's where the sun is directly overhead, and it hits more of the northern hemisphere, not straight on. It's more of an oblique angle that it's hitting it, but it's still getting full sunlight during the day. The interesting thing about that Earth's tilt is it varies between 21 or 22.1 degrees and 24.5 degrees. So right now we're kind of in between those two red lines at 23.5 degrees. And we're on our way towards 22.1. If you stick around for another 20,000 years, you'll probably be able to experience that. If not, that's sad, but none of us will. But just that little bit of change, it makes a little bit of difference. Anything that goes on in the atmosphere, just the slightest little twitch or change can make a difference in the weather. So this obliquity angle, or the Earth's axial tilt, is actually changing at about 0.00001 degrees every 30 days. And what that's causing is the Arctic Circle to move further north and the Antarctic Circle to move a little further south. And we're about 4 feet closer to the poles with the Arctic Circle than we were a month ago. If you do a little bit of math, I told you there wouldn't be any calculus. I didn't say anything about math. This is just straight up math. That's about 48 feet a year, if I did my math right, or 4,800 feet in 100 years. So about a mile, and I'll steal a term from geology, the Arctic Circle is creeping further north. And the Antarctic Circle is creeping further south at a very, very slow progression, but it's doing it. Now, I don't want to call out my wife because I told her she's nuts when she told me, because we live on Snow King, side of the hill. And from, I don't know, late November till early mid-January, we don't get any sun peeking over the ridge line at Snow King. None. But in the last 4 or 5 years, we've lived there for almost 40 years in the same house. We get a little bit of sun and it comes through the skylight in the kitchen. And she goes, see, that never happened before this late in the fall. See, that never happened this early in the winter. So it was narrowing. And I said, nah, it's because they cut all those trees down to make that road going up Snow King. And then I kind of looked at Snow King and I thought, their road's over there. Where the sun is over here, not where they disturbed any trees. So it's perceptible. If you hang around 40 years in the same spot and keep looking at the sun, and she's very observant, but she's not crazy. Okay. Anyway, got a little bit of creep going this way. We also have a little bit of creep of the Tropic of Cancer and Tropic of Capricorn moving closer to the equator. So that opens up what we call the temperate zone in between, gets a little wider. And that's where we live, is in between those two zones. So if we tilted all the way straight up and went around we revolve around the sun, right? We didn't forget that part yet. Then it would be kind of evenly heated. It'd be more like March and September all year long, that kind of thing. Okay. So, and I don't know, some people say, these are just, random observations, that spring's coming earlier and fall comes later. Maybe that's part of this creep. I don't know. And there's nothing scientific about saying that. But I'll just throw that out because it's just observations. So that's the first thing we need to consider when we're looking at the atmosphere and our weather, what's making weather happen. is the tilt of the Earth. The second thing would be the uneven heating of land versus ocean. In general, the Earth is about 70% water or ocean and 30% land. Land heats up and cools down more readily than water does. So the land will get hotter during the day on a sunny, warm summer day, and the ocean will heat up much more slowly. And we know that intuitively. Have you ever been to the beach, middle of the day, and the sun's beating down on the sand, and you get up out of your chair and you start walking on the sand and go, whoa, that's hot. What do? You run to the water, right? Cool off. Well, that sand and that water right next to each other, they've both been getting the same amount of solar radiation all day, but the land is hotter than blazes and the water cools you off. Okay, so those two substances next to each other create a big difference in temperature, and that's key to forming the weather. Okay, the reality here, this is just in general. If you look at the northern hemisphere versus the southern hemisphere, the northern hemisphere is about 60% water, 40% land, so a little bit more land mass than the southern hemisphere, which is 80% water and only 20% land mass in the whole of the southern hemisphere. So the heating and cooling exchanges between land and water are much greater in the northern hemisphere than they would be in the southern hemisphere. Okay? The third thing that plays into this is ocean circulations. And if you just look at see the USA in the middle, just look at the Pacific Ocean and the Atlantic Ocean, and imagine the circulations both being clockwise in both oceans. So on the western side of the Pacific, you get a warm current traveling north. Same thing on the western side of the Atlantic, you get a warm current flowing up the east coast, known as the Gulf Stream. And then on the eastern side of the Pacific and the eastern side of the Atlantic, you have a colder return circulation of the sea surface temperatures in the ocean coming down that side. So there's all this mixing going on and moving warmer and colder air across both of those oceans. The bigger picture looks like this. The red line is the equator. And it's a little bit more complicated, so don't try to memorize this as you're looking at it. But one thing that does stick out here at the bottom of the picture, the blue is the Antarctic circumpolar current that just circles Antarctica. And every once in a while, you'll get a warmer current, which is in the pink, pushing down through that circumpolar current. And that's what kind of whittles away at the sea ice down there in Antarctica. One thing I should probably go back to here is that a difference in the two, as far as weather goes, is the northern hemisphere, most of the ice is sea ice. It sits over water. So that'll erode away. Greenland, it doesn't. That's more like Antarctica, but Antarctica is just huge land mass of ice. And then you have the sea ice around the periphery of that. So the ocean temperature, warmer water will whittle away at those, and that changes where the warmest and coldest air is at the surface. Right? The other thing about the oceans to keep in mind is they're turning over. They do it on a periodic basis, but short-term and long-term air temperatures are changing in the oceans because of a vertical circulation that I won't elaborate on here. So it's the combo of 1, 2, and 3, which I just described. And if you're paying attention, you'll remember what 1, 2, and 3 are. If you didn't, it's the tilt of the Earth, the difference between the differential heating between land and ocean, and then the ocean currents. All of those things develop air masses, which are constantly moving around the planet. But, up in the Arctic, it's usually a cold air mass. Maybe in the Gulf of Alaska, it'll be a kind of a cool ocean water air mass. You also have dry air masses over deserts, and then you have warm oceans down in the subtropical regions. And all of that kind of leads to the weather that we see around the globe. It's basically the collision of different air masses bumping up against each other that cause the weather. And where they're carried by the upper level winds is going to determine what kind of weather we get, or weather in different places around the globe. Right? So air masses are characterized by two main things: their temperature and their humidity. And temperature and humidity are both relative. Everything in meteorology is relative. Pressure's relative. I got high pressure here, I got low pressure there. I got warm temperatures here, I got cold temperatures there. How cold? Well, that's relative to the time of year, the location, the latitude, things like that. Okay. So just remember, every variable in meteorology is not only variable, but it's relative to something nearby. Right. So let's start out with a cold, dry air mass at the North Pole. Can everybody agree that it's probably like that up there, or do we need a field trip? All right. It'd be great. But if I was going to take a field trip, I'd go the other way. I'd go down to the tropics right now, where it's usually warm and generally wet. I mean, there's dry areas for sure, but there's a lot of moisture just because there's a lot of convection. There's a lot of upward motion that's lifting the air. And so that it contains a lot more moisture throughout the year in tropical regions than it does in polar regions. So if you go in between there, like I said, in the Gulf of Alaska, you might characterize that as cold and wet. If you go down to the desert Southwest, you might characterize that as warm and dry. And so when I have a cold, dry air mass up by the poles, that's moving southward from the pole. And warm, moist air is moving northward from the subtropical regions or the equatorial region. And where those two different air masses collide is where you'll get weather forming. We would refer to that boundary as a front, because those air masses don't necessarily like to mix together very well, at least not initially. And the bigger the difference in the characteristics of those air masses, the stronger the storm can be. So the warmer and moister the air that's coming from the south, meeting colder and drier air from the north, the more powerful a storm you can make, right? If it was all kind of, cool and semi-dry and lukewarm and semi-moist, it wouldn't make a big storm, okay? So you want to have big differences in those characteristics. So I'll walk through how a storm develops from this. It starts with this. It starts with a boundary between, we'll just say, cold and warm air. Cold air to the south, warm air to the north. This is what's known as cyclogenesis. In other words, the development or genesis of a cyclone. And the cyclone is a low pressure center, whether it's northern hemisphere or southern hemisphere. But I'm going to stick with northern hemisphere example here, where as this goes along, the cold air and the warm air are still separated, but something causes a ripple in the atmosphere, whether it's a big wave or running into some landmass or something like that, that causes the air to turn. And there's always angular momentum in the atmosphere too, because the Earth is turning. So once you start pushing it in a direction, it'll continue to spin. So if you push that into a counterclockwise circulation, it'll develop itself into a low pressure center. I still have cold air to the north, but now it's moving further south, and I have warm air in the south, and it's starting to circulate further north. But there's still boundaries between them. Cold front and a warm front would be what that's called, and low pressure in the center of it. And this is just because of the difference in temperature. I'm not talking about differences in humidity. It can just be temperature. And maybe you've all experienced the same thing on a really small scale. Have you ever been in, you see them around here in the summertime, in the sagebrush, and you'll see them in the desert. Little dust devils that form, just little vortex that just spins up and just shoots dust up into the air. But you can see it turning. It can actually turn in either direction. But all that is at the surface of the ground, it's been heated. It has to be on a pretty warm day, and the ground's generally pretty dry where you get a dust devil. But you build up a really low level inversion. In other words, it's really hot at the surface, but just above it, the air is progressively a little bit cooler. So I have a difference in air masses there on a micro scale. And you move that air along and it hits a piece of sagebrush or a boulder, and it gets spun one way or the other, and the angular momentum takes over and it just whips it up into basically a small low pressure center that raises the air upward. The other example I would use, and you don't see it so much here at the target, but if you go to a bigger city like Salt Lake and you go to a Walmart or a Costco or something, there's always a corner of the building that is shaded. Like maybe at the entrance, depending on which way the building's oriented, there's always this corner that is in the shade. And then you got this huge parking lot that's black asphalt, right? Adjacent to that. So that air mass is heating up in the parking lot, but it's staying relatively cooler in that corner. And every once in a while, you'll see this little garbage tornado build up where you got plastic bags flying and dust and who knows what else, cigarette butts. And have anybody not seen that before? You got to take more field trips to a big city with Walmarts on a warm day, okay? That's another example of two different air masses, a cooler air mass in the shaded corner and a very warm air mass out in the parking lot, okay? So anyway, this process goes on until eventually the colder air that's traveling south overtakes the warmer air that's traveling north, and the fronts start to occlude. That's the purple line there, to the point that now it's starting to mix itself together. And just to keep the terms simple. And then the final stage of cyclogenesis would be a separation of those air masses, or, you know, there's not as big a distinction. It's just kind of cool to the north and kind of lukewarm to the south. Okay. So that's how storms develop, but where do they form and why do they form there would be the next thing I would propose showing you. Okay, that's a big storm right off the Pacific Northwest coast. So let's start with this and go back to the North Pole. And we know it's cold up there most of the time, relatively colder than anywhere else on Earth, right? And again, I'm going to concentrate more on the northern hemisphere here and not confuse you with the southern hemisphere, but it's a very similar pattern that develops. Right? And then cold air is dense, right? Denser than warm air? Yes, that would be the correct answer. I know it's not a physics class, but I'll throw the answers to you. So when I have cold, dense air that's building up and sinking, I'll generally build up high pressure over the North Pole. Okay? Where the tropics are, where it's warm air likes to rise instead of sink. So as warm air rises off the surface, it's removing a volume of air upward into the atmosphere. So what it does at the surface is it lowers the pressure. So around the equator, in general, you have low pressure kind of circling the globe, or you know, kind of a belt of low pressure that surrounds the globe in general. Okay, all that cold air up at the North Pole is going to start working its way south. There's nowhere else to go except creep to the south, and eventually it'll warm up enough as it gets further south that it'll start to rise. Where that starts to rise will form another area of low pressure around the globe. That warm air, which is rising up off the equator, will spread out both north and south aloft, in other words, in the higher levels in the atmosphere, until it moves far enough north that it cools and starts to sink, and sinking air builds up high pressure. So what I end up with around the globe is sort of these vertical circulation patterns and alternating areas of high and low pressure. So I have high pressure at the North Pole, low pressure around 60 degrees north, give or take several degrees of latitude, high pressure around 30 degrees, and low pressure at the equator. All right. So where do storms form? What's that? Well, where the air's coming together, but wherever there's low pressure. Low pressure is a storm. High pressure is generally sinking air and nice weather. That's why if you want to go storm chasing in the winter, go up to the Gulf of Alaska. That's close to 60 degrees north. That's the brewing grounds for storms. If you want nice weather, you go hang out around either side of 30 degrees north, and most of the days you're going to have pretty good weather. You know, that's like Baja, Hawaii, places like that, you know, even Arizona, you know, several degrees either side of that. And if you just want to have thunderstorms all the time, or a lot of the time, or parts of the time, then you go to the equator. But at the same time, this horizontal circulation pattern or the vertical circulation pattern is going on. There's a horizontal circulation pattern going on. Going back to physics, everything in nature moves from high pressure towards low pressure. Do you buy that? Nobody's disputed that for years. Does that make sense to you, John?
Yeah.
Okay. So that means the air is moving from 30 degrees north towards 60 degrees north all the time. But does all of our weather come from the south? Where's most of the storms that we get here come from? Yeah, out of the Pacific, right? So what makes it do a 90-degree turn to the right? It's going like this.
Rotation of the Earth.
Yeah, the rotation of the Earth. So this is known as the Coriolis effect, which if you really want some math and differential equations and all that, you can dive into that one. But take my word for it. In the northern hemisphere, air starts moving from high towards low, and then it turns to the right, okay? So between 30 north and the equator, it's moving from high towards low, and then it's turned to the right. So what we end up with here is the westerlies exist between 30 north and 60 north. That's sort of the temperate zone that we live in. And so most of the weather as it travels around the globe is moving from west towards east. Down in the tropics or subtropics, even including Hawaii, between 30 and 0, everything's moving from east towards west. So those are the trade winds. And that's because it's starting to move from north to south, and then it's turned to the right. And it's always turned to the right in the northern hemisphere. If you want to really confuse your brain, it turns to the left in the southern hemisphere. Okay? I'll try not to go there, but I might. So this Coriolis effect, the turning of the air, is strongest at the pole, north and south pole. At the equator, there is no Coriolis effect. And the reason being, this is if I was looking straight down at the North Pole, and the Earth rotates counterclockwise as you look down at the North Pole. If I were standing on the North Pole right now, this would be my entire day, 24 hours. I haven't moved anywhere, just stood still. But it took me 24 hours to make that rotation. If I was standing on the equator, I'd be standing straight up. There'd be no rotation around me vertically. I'd just be going head over heels around the Earth. The other thing I'd be doing is I'd be moving a lot faster. I'd have to move a lot at a higher rate of speed at the equator to cover that same distance that I did when I was standing here at the North Pole. So it's the difference in speed, the relative speed at the equator, which is 1,040 miles an hour. That's how fast Earth has to turn at the equator to make a 24-hour day. And then as you go north to 30 degrees north, it's 880, and you get to 60 degrees north, it's half that speed of the equator at 520. I won't go into all the physics of this because there's a lot of it, but just take my word for it that that's what causes that turning to the right. And everything initially starts moving from high towards low. It's turned to the right by the Coriolis effect. I'm going to see if I can pull this off. And I want to pull my, I can do this relatively painlessly. You're going to see it. All right, now we seeing that? Zoom seeing that?
Yep.
Got movement here. There's the Gulf of Alaska. There's Hawaii. I got a counterclockwise circulation here. This is a little low pressure, well, fairly good sized low pressure center curling up right here. And I've got another one up here. But if I go down to the tropics, go down to the equator, I don't have any of those little swirlies. I don't have any low pressure centers spinning. Why? There's no Coriolis effect there. So all you get really is just these easterly trade winds either side of the equator. I go further south into the southern hemisphere, and then things spin the other way. So we won't burden you with that right now. Here in the Atlantic, same thing. I've got low pressure, and then I go down by the equator, and it's just these light trade winds. Here's the doldrums right now, where if you're trying to sail a ship off the coast of Africa, the surface winds are almost zero. What are they? 5 knots at the surface. So this is the surface winds that you're looking at here on the globe. Let's talk a little more about those. We'll go back to where we left off here. Okay, so this is kind of the bigger picture. Not quite going all the way to the South Pole. But the one thing I want to point out on here, got the polar easterlies and the westerlies where they collide right there at 60 degrees north. That's where those storms form in our realm up here in this part of the globe. Same thing happens in the southern hemisphere down there between 30 or between up around 60 degrees south. The other thing to notice on here is that over the equator, or the warmer regions of the planet that are getting more direct sunlight, the atmosphere is actually thicker. So that 50,000 feet is sort of an average around the globe, but over the poles, or over the equator, it's thicker, and up near the poles, the atmosphere is thinner. Okay. That's really all I wanted to mention about that. So when you get into thinking about trying to forecast weather, you have to think in 4 dimensions. You got to think changes that are going on in the vertical and keep track of that. You got to keep track of changes from north to south and from east to west. And then you have to move all that through time. So it becomes a very 4-dimensional problem when you're looking at how the weather's changing. The way it changes in the vertical is pretty simple. And I think most people, it's intuitive, especially living here in the mountains where we get to go ride up the tram and experience colder temperatures on some days than we have in the valley. We've been back and forth so much the last month that it's almost hard to keep track of what day, how to dress, especially if you're going skiing, because it might be, 30 degrees in the valley and it might be 15 on top. This morning, it was pretty even. It was like single digits in the valley, single digits at 10,000 feet, not much change. But in general, the atmosphere will change and get colder as you go up in elevation. So as you go up in elevation, and that's on the right-hand side here in feet and meters. On the left-hand side, that's the pressure in millibars. So down near the sea level, it's a little over 1,000 millibars in general on average. As you go up in altitude, the pressure decreases. At about 500 millibars or 18,000 feet, that's about the midway point of the atmosphere. If you're standing on top of Denali, or at 18,000 feet on the side of Mount McKinley or Denali, whichever you want to call it. I've climbed it when it was named both. But as you're standing there, you only have half the weight of the atmosphere above you. In other words, compared to me standing at sea level, you got the entire atmosphere on your shoulders. It's heavy because pressure's weight. You get to 18,000 feet and it's like, what a relief. I've got half the weight of the atmosphere off of me. I feel so light, I can move around like I'm on the moon. Except for your oxygen's cut way back. So that sort of slows you down a little bit. So again, 18,000 feet is sort of the midway point. And that's 500 millibars is a level in the atmosphere that we analyze quite frequently for the general overall weather pattern because it's up and out of the effects of friction at the surface. So it's kind of undisturbed, except for, when it bumps into Denali. But up above that, the other level we look at quite frequently is the jet stream level. And that's going to be between 30 and 35,000 feet, or between 300 and 250 millibars. Those are kind of key levels in the upper atmosphere that we pay attention to. So that's how, just in brief, how things change in the vertical. They also change in the horizontal. And again, going back to those air masses where I have different characteristics from one area to another. Like that side of the room is cold and dry, this side's warm and moist. But when I have differences like that, especially in temperature, if I have a big difference in temperature across this room, I'm going to have a big difference in pressure. And that's kind of key because where I have bigger the difference in pressure, the bigger the pressure gradient from one side of the Pacific to the other, or from the Gulf of Alaska to the Pacific Northwest coast, whatever the case may be, from the West Coast to the Rockies. The bigger the difference in pressure, the stronger the pressure gradient is, and the faster the winds will blow. But then you got to throw in which way the wind's going to come from. So you throw in the Coriolis effect, and that'll tell you. So here's a little simple diagram that I drew many years ago. I don't even know. This was like pre-PowerPoint. I probably did this on an overhead slide and then took a picture of it. Anyway, this nice square state, sort of an oblique view. So like Wyoming. And then I got Cowboy Joe standing there in Laramie or Cheyenne, and he's just hanging out watching the clouds go by. We got high pressure to the west, low pressure to the east of Cowboy Joe. And the first thing that happens is the air starts moving from high towards low, right? That's the pressure gradient force. Down near the surface where Cowboy Joe is, you got some friction. So that'll slow the wind down a little bit, be a little faster aloft and slower at the surface. And then the third thing that happens is as it starts moving from high towards low, it gets turned to the right in the northern hemisphere. Well, anytime anything starts moving in a curved path, there's going to be some centrifugal force involved. So when I take that corner too fast to the right, which way am I getting thrown? Against the driver's door. I turn too far to the left real hard, and my wife's joining me in the driver's seat from the passenger seat, right? So I'm ending up in her lap, I should say. So I'm getting thrown to the outside of that curved path. So what Cowboy Joe observes here when he's looking at the clouds is the resultant wind direction is kind of out of the northwest. If he's out in the plains and away from the mountains, if that's the surface wind he's experiencing, then what he can do is he can put his back to the wind and point to the left, and low pressure will always be to his left. Here in the mountains, what we have to do is we have to watch the clouds go by overhead. And so if they're moving this way overhead of me, then low pressure will be to the left. Okay? So it's always low to the left with your back to the wind. Okay? So let's take an area of high pressure and an area of low pressure. Highest pressure is where the big blue H is, and lowest pressure is where the big red L is. And air is going to start moving out from high towards low. It'll get turned to the right, and then it'll be balanced by the centrifugal force to the outside of the curved path. So under high pressure, which is a lot of sinking air, I'm going to end up with a clockwise flow around high pressure, and the air is diverging away from that center. Okay, so it's sinking, diverging away from the center. Outside of the red L, everything else outside of those circles is all higher pressure. So that's moving in towards the low. It's again turned to the right and then pulled back to the outside of the curved path by centrifugal force. So what you end up with around low pressure is a counterclockwise flow or direction and converging flow into the center of the low. And anytime I converge air at the surface like that into a low pressure center, it has nowhere else to go but up. and up is key to making weather. If you're not making the air go up somehow, you won't have any weather. The only kind of weather you'll get when the air is sinking is fog in the valley. Air has to be moving up. As it moves up, it cools. If there's any moisture in the air, it'll condense, and then it'll make clouds, and then it'll maybe precipitate, if you can keep all those processes going. Right? So low pressure is one way to lift the atmosphere. A hill or a ridge, as we would call it, is what you would want to visualize there. This is a two-dimensional map, flat Earth, but think of it in a third dimension. That under that high pressure center, it's coming out of the screen. The atmosphere's deeper. It's got more atmosphere build up. There's higher pressure, more weight to the atmosphere. Where the low pressure is more like a hole in the atmosphere, or a trough, a low point in the atmosphere. If you want to look at it this way, and you got sinking air under high pressure and rising air in the center of low pressure. But if you want to look at it, how it would look in the vertical, it'd be more like this, where if I'm underneath high pressure, right under the center of it, that's where the atmosphere is the tallest, where I have the most pressure pushing down on me. If I'm standing in low pressure, or under low pressure, I'd have less atmosphere. So all that air around the high pressure ridge is sinking into the trough or the valley of low pressure. And then again, it doesn't have anywhere to go once it converges into the center of that low, but up. And that's what causes the lift, and that's what causes clouds to form. Okay. Got it? Yeah, you can get all this stuff, in a book. I could recommend one for you. One easy way to remember which way high pressure and low pressure spin in the northern hemisphere is, I'll use a screw analogy. If you are trying to sink a screw into the wood, you have to turn it clockwise. If you want to raise the screw out of the wood, you have to turn it counterclockwise. So counterclockwise, rising air, clockwise, sinking air. Does that make sense? Yeah. Okay. One other way you could remember this is you just take your right hand, put your thumb up, curl your fingers in like this, look down at that. That's a counterclockwise rotation. Upward motion. Doesn't mean good weather. It just means rising air. Right hand, flip it over, curl your fingers in towards your wrist. That's a clockwise rotation. I'm not much of a Gumby myself, not very flexible. And your thumb's pointing down. So that's clockwise circulation, high pressure, sinking air, right? If you do happen to travel to the southern hemisphere and you get down around New Zealand, use your left hand and it will tell you the same thing. That's low pressure. That's high pressure. It's the opposite. Okay? I haven't been to New Zealand personally, but I plan on going there because what I want to find out is if their screws go in the different directions. So I can write that trip off. All right. So we depict pressure on a weather map with isobars and lines of equal pressure. They look like this on a flat map. Flat Earth, right? Flat weather map, surface weather map, the white lines are the isobars. And you read it just like you do a topographic map. Lines of equal elevation on a map, on a topographic map. So on a topographic map, if I have a bunch of lines that are really close together, like I have up here, what does that mean? Yeah, steep. In this case, in a weather map, it means you have a steep pressure gradient, strong pressure gradient. So where the lines are really close together, the winds are going to blow faster. Same with up here. Where the lines are spread apart, that'd be like a saddle or a col or some big open meadow. My gradient isn't very great at all, so I would have really low surface wind speeds wherever the lines are really far apart, right? And then I also have my high and low pressure areas. So those are my hills or mountains, and then my L's or my valleys on the surface map. Okay? Read it the same way, no different. Bump it up a level, up to that mid-level of the atmosphere at 500 millibars or 18,000 feet. And things straighten out a little bit. They're not quite as complicated as down here at the surface because I don't have friction to worry about and elevation changes and all that stuff. I'm up here in the free atmosphere, just cruising along. This is a little bit different. What's plotted on here is the height of the 500 millibar level in the atmosphere. So that changes. So under high pressure, the height will be higher. Under low pressure, the height will be lower. But just look at it the same way as you do any contour map like this. So here's Wyoming, just for reference. We've got all of North America going on here underneath, but just concentrate on the blue lines. Those are the height lines, or what we'll determine as the pressure plot on the 500 millibar map, the height of that pressure level. So that's a ridge of high pressure in the at 500 millibars. There's another ridge of high pressure. And then I have two troughs of low pressure on this particular map. This is kind of a unique map because I've got even spacing of the alternating high and low pressure all across North America, from the Pacific to the Atlantic. And the amplitude of those ridges and troughs, they're all about the same. Rarely will you see it just like that. That's why I love this map. If it was just like this and stayed like this, it'd be easy, right? Kind of, relatively. So if you just follow the contour lines, and trace it out, that's the flow of the atmosphere in the upper levels. So weather's going to naturally follow that pattern. And so off the West Coast, it's moving from south to north. And then up in Canada and into the upper Midwest, it's moving from north to south. And then along the East Coast, it's moving from south to north again as it traces around the troughs and ridges. All right. And this is going on all day, every day around the globe. It's just the pattern's different. And we just have to figure out what pattern we're in and how that pattern's going to shift through time. Bump up one more level to jet stream level. And this is kind of a complicated looking map with all the little wind barbs on it, but just pay attention to the color contours of speed, which is what the scale is at the bottom there. And so if you're looking down here, this is the scale. And up here, I've got fastest wind speeds here. That's what the jet stream, how the jet stream is defined. It's the area of the fastest winds in the upper levels of the atmosphere. And these winds, where it's kind of red and pink here, are all blowing over 100 knots at 30,000 feet. The other thing the jet stream is it's a dividing line between where the coldest air and the warmest air in the atmosphere is. So on the north side or poleward side of that jet is where the coldest air is. And on the south side of that is where the warmest air is. And that warm air can get transported by that jet stream all the way up into the Northwest Territories sometimes, depending on how tall that ridge of high pressure is. I can still see troughs and ridges in here as well from that jet stream pattern. And the jet stream kind of guides the weather down at the surface. And then all of this, of course, moves along in the westerlies. We're between 30 and 60 degrees north. It's pretty simple, isn't it? This meteorology stuff. Piece of cake. Piece of cake. The other thing, with the tilt of the earth and the seasons, that jet stream's going to, oh yeah.
Anybody bring a bike to the library? Yeah, we're closing, so it's gonna be locked in overnight. In the future, you can park outside. Yes.
I won't say anything prophetic till you get back. But the jet stream will migrate from north to south with the seasons and the tilt of the earth. So in the wintertime, it's further south. In the summertime, it's further north. It's also much stronger in the wintertime because there's a bigger difference in temperature between the northern latitudes and the southern latitudes. In the summer, when you got more even heating across the northern hemisphere, the difference in temperature between the tropics and say 60 degrees north is not as great as it is during the winter months. It's much, much colder, usually in the winter months, up around 60 degrees north, going around the globe. So the jet stream is generally stronger, you have stronger winds, things like that. So let's look at where the jet stream is, and we can look at that until that guy gets back. I'm gonna go there. I'm gonna go there. And there. didn't take too long, did it? Moving? All right. So just a little reference point right here. That's the Great Salt Lake. So we're just kind of right about there. And this is the jet stream pattern. Kind of complicated today. This is right now, actually. This is off a computer model, but it's, you know, a global model that's depicting where the jet stream is. So right up here, that's 160, let's go a little further. About 164 knots, I think, where the strong, 195 knots right here. If you want that in miles per hour, it'd be 225 miles an hour. If I move the globe around here and look across the Pacific, there's quite a stream of moisture coming off of Asia. Very broad jet, very strong jet, 173 miles an hour right there, and 177 miles an hour at, this is at about 35,000 feet in the atmosphere. But I can still see the troughs and the ridges, kind of a complex ridge pattern over off the west coast, and then kind of over us right now. We've got kind of a northerly flow. That's what's bringing colder air further south. And then that's actually extending all the way, the jets all the way down into Baja. And then you move over to the eastern part of the United States. This was a cold, low pressure that was actually pushing down into the southeastern United States just a couple days ago. And now it's kind of moved off up here. And then big area of high pressure right here where I want to be right now in the Caribbean. Wind speeds at 35,000 feet are 3 miles an hour. Surface winds are like 5, and at 35,000 feet, it's 3 miles an hour. That's insane. Pretty calm. All right. So that's the jet stream. Back to business at hand. We are back in business. All right. Does that explain the weather, how it works? All right. Easy. That part's easy. This part, more complicated. Talking about gas and the gases in the atmosphere and how they have, what kind of control do they have over the weather? I mean, there's nobody in this room, I don't think, that hasn't heard that there's some sort of gas that hangs around that controls our temperature. Am I right or wrong? What gas is that? Well, yeah, that's the correct answer. So all of these gases are what make up our atmosphere. The kind of single atom ones, like nitrogen and argon and then oxygen, of course, those are not greenhouse gases. But these other ones, water vapor, carbon dioxide, methane, ozone, and nitrous oxide are all considered greenhouse gases. What does that mean? It's the greenhouse effect. It's an effect. It's not the Earth doesn't really act like a greenhouse because the Earth is open, has open doors, and has convection. The idea of a greenhouse is you're containing the air within a glass space so that sun comes through, but there's no convection to mix that air. So it just keeps it nice and warm and toasty inside of there, right? But the Earth is open-doored, but it does have a cap to it. It has a roof. That's the top of the troposphere. And that's kind of where all of these, well, the gases exist throughout the atmosphere, but it's the upper levels of the atmosphere that kind of cap that off and cause this gas problem that we have. And I'm gonna talk about I'm gonna discount nitrous oxide, NO2, and ozone because they're in very small quantities anyway, but they do have some effect. I'll forget about those. Methane, we've solved that problem now, I think. Jeff Bezos has just come out with a shot for cows and farm animals and some feed that'll make them burp and fart less. So I think we're good. We don't have to worry about methane as much. Methane also has a shorter shelf life in the atmosphere than, say, carbon dioxide. So there's all the different greenhouse gases. And basically what's going on is the sun's penetrating in and warming the earth. Okay? The sun doesn't necessarily warm the atmosphere. It warms the surface, and then that heat moves upward through the atmosphere. Very little heating goes on as it's passing through the atmosphere to the surface. But once it's re-emitted as long-wave radiation back towards space, the greenhouse gases will trap some of that heat and re-emit it back towards the surface. It actually emits it in all directions, upward towards space, sideways, and down. And it's been calculated that if we didn't have any greenhouse gases, the Earth would be way cooler. So all of these things, all of these gases occur naturally. They naturally occur without us. If we weren't here, they'd still be there. We'd still have a greenhouse effect, and it would help keep the surface of the planet comfortable in most places. Without them, the average temperature around the Earth would be like 0 degrees Fahrenheit. It'd be uninhabitable basically everywhere. That would include the tropics to a point, because it's average speed, or average temperature. So this is a simplified version. This is a more complex version, and I don't have time to discuss all that, and I won't belabor you with it. This is what we call the physics wheel of pain. Just all the different things that go on just to determine where there's going to be moisture, what the temperature is going to be, things like that. Okay? So now here's your quiz. I'm going to move away from the screen here for a second, just so I can get some exercise. That's okay. So pay attention. All right. First question. What's the most abundant greenhouse gas in the atmosphere? And John, don't answer. CO2? Water vapor? It's water vapor. Okay? It's the most abundant, and it's a greenhouse gas. Let's go to CO2. Small quantity, but where's most of the CO2 come from? Where's it produced? In the Amazon? They're absorbing it. Trees, they absorb it. We breathe it. Plate tectonics. The ocean. Most of the CO2, something like 93, 95%, something like that, of the CO2 in the atmosphere right now is emitted from the oceans. Last question, trivia for most of you. Remember having a car that didn't have a catalytic converter? And scientific people don't answer, but the other people who, what's your guess? What does a catalytic converter do? Converts something. Yeah, you're getting close. Yeah, you're close. What it does is it converts carbon monoxide into carbon dioxide. So in the late 70s, when they mandated that we had to have catalytic converters on every automobile built from that point forward, and we still have them, we helped clean up our atmosphere and remove a poisonous gas, carbon monoxide, or at least quite a quantity of it, much more. I mean, they used to just spit out a lot of CO and no CO2, really, not much. Now, most of what comes out of your tailpipe is CO2 rather than CO or carbon monoxide, which is a poisonous gas. It's a pollutant. Is carbon dioxide a pollutant? I like it. Because every time I exhale, I like it. If I quit spewing CO2, I'm dead. That's just natural CO2, right? Burning fossil fuels does put a lot of excess CO2 into the atmosphere, but how much is the big question. But most of the CO2 that we have in the atmosphere is beneficial to plant growth because plants absorb it. And so here's a few fast facts about greenhouse gas. Water vapor is the biggest contributor to the greenhouse effect. About 87 and 95% because it's a variable gas. And that would include the water vapor that's invisible and then the clouds that we see, which are visible. So any contribution of H2O there is the leading greenhouse gas producer for us. The contribution that carbon dioxide adds to this is about 4 to 5%. Of that 4 to 5% of the total carbon dioxide that's produced in the atmosphere, 4% of that total is what we emit. Not 4% overall, but 4% of the 4 or 5%, which means that its contribution, the human contribution to the greenhouse effect is 0.16 to 0.20%. This is just a summary of the calculations done by a Greek engineer, environmental engineer in Athens, University of Athens. It was just published in October, which really put it in perspective for me. Well, because the biggest problem we have when we talk about carbon dioxide or any of the natural gases that we have, like methane, how much of that is natural and how much of that is what we're emitting. And if you press any climate scientist to tell you how, when you measure carbon dioxide in the atmosphere, which we do, how much of that is natural and how much of that is from us? Well, this kind of gives you a ballpark. And it's really the only study I've seen that actually answers that question that has not been answered before in my mind satisfactorily. I'll go back to that quiz I gave you. I've given that same exact quiz to guys that have masters in environmental science and masters in environmental engineering, and neither of them could answer those 3 questions correctly. So somebody's missing the boat when it comes to educating environmental science people. All right, let me just, I'm almost done here. So I'm not saying that we're not contributing to warming. There is warming going on. These are the sea surface temperatures. This is all from satellite data, and that only extends back to 1979. That's when we have the first decent satellites up. We upgraded those in the mid 2010s to more sophisticated satellites that measure temperature on Earth. And this is just sea surface temperatures between 60 north and 60 south, because the satellites can't see. They have a very oblique view north of 60. So they can't really measure what's going on at the poles as well. So in where most people live, between 60 and the equator and south of that. So this is both north and south hemispheres. You can see that back in the 80s, it was much cooler. And then by the last couple of years, it spiked to as high as since the beginning of recordings in 1979. But that bracket on the left, that's just 1 degree of Celsius. Okay. If you look at this is the satellite data through the end of December 24. Same thing. Back in the 80s, the oceans, the whole planet, again between 60 north and south, including land temperatures measured by the satellite that's going overhead, was cooler. And then kind of rolled along and then spiked up a little bit and then really spiked out here the last 2 years. That's very curious to me. Why did that spike? Careful. What the Fahrenheit's going on? That's my question. Even though these are in Celsius. Again, I'm not looking at a huge, the graph makes it look bigger, but you're in 0.2 of a degree increments, which my thermometer doesn't do that well measuring that. anyway, we know that CO2 has been rising steadily. We've only been measuring at these 4 stations. The oldest one's Mauna Loa, that goes back to 1959. And then the other ones came on later in the 70s. So this is all those stations. And, you know, we've had about 100 parts per million of increase in CO2 around the globe, if you want to include the whole globe, by just these 4 stations. And they're all out kind of near the ocean. You know, that's somewhat significant. That's just been a steady rise, even though temperatures kind of go up and down. And you can see on there, especially Barrow, which is the blue plot, it goes, you know, swings seasonally much bigger than the other ones that are closer to the tropics. I don't know about Samoa and the South Pole, but I do know about the Mauna Loa one, which sits on top of the mountain. Mauna Loa, I don't know what it is, close to 14,000 feet. And it is an active volcano. But there's the locations, those green X's are the locations of those monitoring systems. So they're all out in the oceans. But warm oceans emit more CO2 into the atmosphere. Cold oceans absorb CO2. And so when we have had colder oceans, it should have been absorbing a little more CO2 and not emitting or releasing as much. Compare January 1st, 2025 to January 1st, 1985. The blue means, and this is an anomalous temperature. In other words, off the baseline 1991 to 2020, which is the same as this chart here. The average line in the middle, the 0 line there, I should say, is the median temperature, and it's the departure from that average of 1991 to 2020. This is the same thing plotted on here, but a lot more areas of warm temperature in the ocean today than we had 50 years ago. And this changes. It changes through time, but we don't have any good data like this any earlier than 1979. But it's definitely was a colder period in the mid 80s when that was going on. So here's some unpopular science, not like the magazine Popular Science. And this is things that many people just don't know, but these are true facts. Temperature changes will precede changes in the CO2. In other words, the increase in CO2 throughout history occurs after the temperature increases. CO2 decreases after temperatures decrease. And you see this in the paleo records, proxy records, and I'll show you an example of that. That's point 1. Point 2 is, and we already kind of answered this, carbon dioxide is not the main control knob on the Earth's thermostat. Water vapor is. There's so much more water vapor. And I'll show you one chart of that and we're done. So this is a ice core in Antarctica, because it's got millions of years of ice buildup. This is going back hundreds of thousands of years. The interesting thing on this, temperature on the top, carbon dioxide in the middle, and dust concentration, which they can determine from the ice core too, if there's dust at certain levels in that ice core. And I drew black lines all the way up from the bottom to where the temperature peaked in all of these thousands of year periods, hundreds of thousands of years periods, going backwards from this ice core. And the most glaring thing to me is that in each case, the temperature spiked and then the carbon dioxide level spiked. The other thing that's kind of interesting is that when we got dust in the core, it was immediately after that the temperature spiked, which may mean that maybe the world was under a drought period. So there's a lot more dust in the air and it got deposited in Antarctica. Not much snowfall going on down there, not most of the time anyway. But more dust in the atmosphere caused the temperatures to go up. Temperatures go up, carbon dioxide level went up. And it makes sense to me because most of the sensors that we're looking at from the real time are all out by the oceans. right next to where all that carbon dioxide is getting released. Not to say that we're not putting it out there, and not to say that we shouldn't be reducing what we emit, but nature does a really good job of emitting quite a bit of it as we go on. So there's your contribution from water vapor, including clouds. And, we expire some, there's some man-made water vapor that wouldn't be considered natural in the atmosphere. If we all drove hydrogen vehicles, then we'd be putting more water vapor into the atmosphere. Not a good idea. Don't let anybody talk you into buying one of those rigs. Because what you get out of the exhaust from a hydrogen vehicle is water vapor. We're not going to help things, okay? And then all the other ones, the contributions is much smaller. So it's water vapor. And I think that's what caused the spike, was an increase in water vapor. And geologists will love this, from an underwater volcano, Hunga Tonga, in the South Pacific in January of 2022. Scientists were all over this. And there's the location of Hunga Tonga on the map. They knew that if you put excess water vapor into upper levels of the atmosphere, and this water vapor went all the way up to the stratosphere through the top of our weather atmosphere, the troposphere. And so it's hanging around up there, and it's spread out, and it circled the globe. So by 2023, 2024, that's when we saw this unusual spike in our temperatures. Greenhouse effect, yes, caused by more water vapor. It's estimated that, and this is, studies that are still going on, but the latest one estimated that we increase the amount of water vapor in the stratosphere, this is invisible, by 13%. And it'll take up to 5 years for that to all kind of dissipate and calm down. So I'd expect another year or two of, warmer than normal oceans, warmer than normal temperatures around the globe, and mainly caused by that volcano. If it was an above ground volcano, it would put up what, sulfur dioxide, or who's the volcanologist? Where's Peter Ward when I need him? And that has an opposite effect. When we've had big, like Pinatubo, several years after that, the temperatures cooled quite a bit because there was a lot of sulfur dioxide. It wasn't a greenhouse gas. It was actually, the same with the dust. Yeah, it reflects the heat that's coming in. So all of these greenhouse gases are invisible, so they let all the light through, let all the sun's energy through, but they don't let it all go back out. And that's the key to warming the temperature. And we see that just on a daily basis with the amount of clouds we have. Clear day, more sunshine to heat the earth better. Not necessarily today, because it was cold from top to bottom. But, if it's a cloudy day, temperatures stay cooler. If it's a cloudy night, temperatures stay warmer overnight. If it's a clear night, like was last night and probably tonight, more radiation can go out and the temperatures at the surface will cool down. We know that's just on our observational level. Okay? So water vapor, man, that's the key to life and the weather and the temperatures and everything we do on Earth. All right, questions? Sorry, I ran just a little long there, but if you got to go, just go. If you don't, yeah, over there.
Water vapor.
Yeah.
This previous one said that, on that previous one said something like 5 years.
Yeah, it'll.
The amount of time that CO2 staying in.
Yes.
Yes. Several hundred.
Yes. Yeah. See it.
Trying to build up CO2. You're actually getting a little bit of warming from that.
Yeah.
And that warming is also going to increase the amount of water vapor that's in the atmosphere at any given time.
It can. Yeah. The question is that carbon dioxide can hang around longer than water vapor in the atmosphere, but this water vapor is in the stratosphere. Most of the carbon dioxide is going to be held in the lower levels of the atmosphere, up to the top of the troposphere. And it does have, I guess the way I could put it is carbon dioxide has a little longer shelf life, but even with the amount that we're adding to it, the Earth is still capable of producing so much more carbon dioxide. And it's also capable of generating more water vapor. And like you said, warmer temperatures, the atmosphere can hold more water. But what you're talking about there is water in the droplet phase. In other words, more clouds. And clouds are really complex. And it's one thing that is the biggest deficiency in all computer models that forecast the weather and climate. They don't account for cloud cover as best they can. So we've had, this was from, I can't remember the dates off the top of my head, but over, say, the last 40 years, there's been a reduction in the amount of cloud cover globally of about 7%. So that allows more heating of the surface of the Earth because you have more days with clear skies in more places. If you increased that cloud cover, where water vapor is turning into water droplets or ice crystals, if you increase that, then you get more cloud cover, which would cool the surface of the Earth because more would be reflected back to, more of the incoming solar radiation would be reflected back to space. It's that complicated. And so even though carbon dioxide, methane's even stronger, but methane has a shorter shelf life in the atmosphere than carbon dioxide does, by my understanding. But they both are greenhouse gases. They both contribute to the greenhouse effect, which is essentially keeping a lid on the outgoing long-wave radiation. But how much of an effect is weighed out in the percentages there. So we're continuing to increase with warmer oceans. We're continuing to increase naturally the amount of CO2 in the atmosphere. But I'm not arguing that we're not contributing a little bit more to that. But when I see a spike like we did the last 2 years, I don't think that we had a giant spike in the amount of CO2 that was emitted by humans to contribute to that. And you can see from the global CO2, it's just a steady rise. And I talked to other scientists about this because when I told you that in the late 70s, we converted to the catalytic converter. And so now we're producing more CO2 out of our cars than we used to back in the 50s. And, but he said that would just be negligible. And I was like, well, it kind of correlates pretty well, right? Timing wise, as far as rising. But remember, correlation is not causation. All right, I can give you all kinds of examples of correlation. There's a great video of a guy who shows a chart of when PowerPoints first started and how the number of PowerPoint presentations increased at the same rate that temperature was increasing. So his point was that PowerPoints, I just created more global warming because of this PowerPoint. I mean to make a joke of that. Yes.
Carbon dioxide, but that's because the temperature is being controlled by the orbital cycles.
Right.
So I think that's
Okay. I'll buy that one. Yeah. Well, what do you think about the change in the tilt of the Earth just that much? What my wife observes.
I think
Yeah, I don't know. There's a multitude of things. You can't forecasting tomorrow's weather or the weather 50 years from now. You can't put your finger on one thing that's going to cause it. It's a multitude of things. You're cutting yourself short if you just think it's one thing.
That really long-term graph, you're saying carbon dioxide went up a little after temperature. What can you explain what after each of those there's a large drop? Can you explain global cooling?
It's just cyclical. I mean, we've just, was it 1850 was the end of the Little Ice Age. You geologists know this better than me, but when I was in college, I got a BS in meteorology, but my minor was in geology. Most of the classes I took were either glaciology or geomorphology courses. So, I mean, because of those changes in the tilt of the earth, the precession, the wobble, the solar output, and there's other explanations besides water vapor that have been proposed for that spike. Another one was that we changed the kind of diesel fuel that ships crossing the ocean use, which used to put out a lot of soot, and that would actually help cool the temperatures in the lower levels of the atmosphere. And now that they've cleaned that up, we get more solar radiation hitting the earth. I don't know about that. I mean, you used to be able on satellite images, you could see the trace of ships going out from the West Coast across the Pacific.
The key thing is to explain the cooling. I mean, if we're going to talk about global warming and you're going to say we shouldn't worry about this, it's temporary.
I'm not saying that it's
what caused the
well
period.
Probably one of the biggest factors that I can think of would be the oceans turning over, which they do. And so like in 85, we had a colder ocean, right? Even prior to that, the oceans were colder. When I first started, the first climatology class I took in college in the late 70s, they were still talking about global cooling. So we had a period from the 50s to the early 80s where they were saying the same things: the gloom and doom, the famine, the droughts, the this, that. Even the CIA did a report because the scientists told them this is critical. We're going to have trouble. It's the same story. It's just reversed. So history repeats itself. The weather does too. The weather cycles like that. So I don't have a great explanation for global cooling other than the oceans turning over and being in a colder phase rather than a warmer phase like we're in right now. Yes.
Probably people. So what are we now in La Nina or El Nino?
We're in a weak La Nina. There's all the factors you need to know: land, water, nice beach, clouds, and then where it's clear, you still have water vapor and the sun. Okay. Let me see if so here's last January. That was an El Nino, warmer than normal temperatures. That's just one way to define it. And then the year before that, it was a weaker La Nina than the winter before that. That was a stronger La Nina, which there's really not a great correlation there, but we had more snow that winter, 21, 22, than we had 22, 23. But 23, 24, it'll come out in the paper tomorrow. You may not believe me, but the stats are in there. The year 2024 was the snowiest winter, second snowiest winter in the town of Jackson on record. There's a lot of years that are missing data, and you'll see the graph in there. But it was the second snowiest winter, 1967. This is an annual, so it's parts of two winters, January to December. Was in 1967, we had roughly 155 inches of snowfall that year. And last year we had 142, 141.7 to be exact. Read all about it.
What's happening in the temperatures of the Bay of Alaska? Gulf of Alaska.
In the Gulf? Well, I don't know what's going on right now.
Talk about that relevant to the weather we see.
Oh, yeah. I mean, it's that clash of the titans. It's the warm air current coming up off, the Western Pacific and colliding with cold air that's, as the ice sheet, the sea ice grows up in Alaska, up in the Arctic, and pushes down through the Bering Sea, then that forces the colder air further south. If the ice doesn't form early or as soon, then that colder air stays a little further north, but that allows that warmer air to move further north, and you get bigger storms in in the Bering Sea. Once the ice extends into the Bering Sea, then it kind of shuts that down there and pushes the development of storms a little further south. So yeah, that's all these things you got to kind of pay attention to and hope that the models are paying attention as well. But yeah, that's always, it's very complicated. I've had enough of that, I'll tell you. Mike.
Forecasting that the West is going to have a warmer winter this year. What is causing that?
It's mainly the weather patterns, and the problem this year, let me get past this because you don't need to know all that. This is January 2025, and this would be a really weak La Nina. So, you know, again, correlations that they tried to do over the years, a lot of those are getting washed away. Like California, a study came out a year ago or so, because they used to say if you had an El Nino, then California would have an increase in snowfall and snowpack, and La Ninas it'd be drier. Well, that's all out the window. They had less than 30% of the El Ninos actually made an above normal snowfall in the Sierra. So that whole concept of thinking is going away. And just because I'm more of a proponent of water vapor being the control knob, you know, don't Galileo me, you know, just don't don't put me away. It's just science, you know. It's yeah.
All right, well, let's have a big hand for Jim.